Any questions or comments? Let me finish this discussion. There's like one more ingredient that I have to talk about, and then I'll try to formulate the problem. So here it seems like rho xy is tau independent and also shape independent, and does that imply that this order is unnecessary to understand at least this effect? And the answer is like no, this order has to be there. Without this order you don't have these plateaus. Okay, we are going to have a long discussion of this, but let me give you the most economical one. So if there is no impurity, then 1 over tau diverges, and we have translationally invariant system. Good. And if the system is translationally invariant, let's start in a lab frame, and let's start the simplest case. There is no electric field, right? E is equal to 0.
In the case of no impurities, do you have tau equals 0 or tau equals?
Like scattering time goes to infinity, right? Like tau is kind of like scattering from one impurity to another, and if you have infinite time to scatter, it means there is no impurity, right? So yeah, it's like 1 over tau. Did I? Yes, I think it's yeah. So there's like infinite time without scattering. That's what it means. So I want to consider the simplest case, like lab frame with no electric field, and there's like B along B times Z. Now let's change the reference frame, boost to a frame that goes with velocity v, let's say in the, you can imagine this to be in the minus y direction. Then in this frame, right, because of like, if you want, this is Lorentz invariance, but I don't think you need Lorentz invariance to see this. What all you need to see is a balance between Lorentz force and electric force. But I think we tried this earlier, so I'm not going to do it again. Let me just write the result. E is equal to minus 1 over C V cross B. B is still BZ. It doesn't change from frame to frame because it's in the transverse direction. And so here J is equal to 0. Here J is going to be minus E and V. So now we are in that frame. And in this frame, right, we didn't do any calculation. This is like a symmetry of the problem. And in this frame, I can look at J cross B is equal to minus E N, this one and this one, V cross B. And you can see this is related to E, right? This V cross B. I can take care of the factors, and I can write this as like E is equal to minus, I think it is plus 1 over E and C J cross B. And what's that? Right, this is charge, this is n, right? I just rewrote everything and try to take care of the factors. And this, I'm going to write it's like B over E and C J cross Z. And this is going to be Jx, Jy, 0 and 0, 0, 1. If you take the determinant, this thing is going to give you B over E and C. X component is Jy, Y component is minus Jx and 0. And from here we have rho as a tensor, this B over E and C, 0, 0 in the diagonal because 1 over tau is infinity. And that's the problem, right? Like tau is infinity, but that doesn't mean rho xx is infinity. Because both rho xx and sigma xx can be 0 because of this matrix structure. It's a little bit subtlety, but it's okay. So this is 1 minus 1. And sigma, if you want, is going to E and C over B, 0 minus 1, 1, 0.
So, for example, this conductor is
Look, this I will come to that. At the moment, imagine it to be an insulator, but it is going to be like topological insulator. So it is a different kind of insulator. And from here, what we see from this calculation is like, right, rho is equal to B over E and C, and there is no quantization. So we derive these results, right, from the symmetry, from going from like one frame to another frame, which is like a symmetry transformation. And this is correct whether you do classical or quantum. There is no change, right? By just taking everything to be quantum is not going to save the day and show you the quantization. So the message here is if you have no impurities, that means translational invariance. That means no whole plateau. So you have to have disorder to observe this. And this is kind of somewhat paradoxical, right? We say that disorder is not important. You see like some robust signature, but we are also saying, oh, you have to have disorder to see this. As long as you have like a tiny disorder, that's all we need. And that's not a problem because even if the technology is like 100 years future of today, there will always be disorder. Nobody can do it, right? There are like billions of atoms and there will be one like imperfection that nobody can just go and check one by one. There will always be disorder in condensed matter systems. I think now I want to start formulating the quantum problem. Quantum dynamics. So this, I think I drive this, you can go back and read those chapters from the book, but let me just quickly sketch to remind you if you forget. We, like to get the quantum mechanics, we start with Lagrangian, 1 over v squared minus E over, last time I think I did with electric and magnetic fields. To simplify the matter, let me just do it like with only magnetic field this time. And here v squared is v dot v, and the important thing here is like a, we don't write the functions, but it depends on both x and y coordinates and no time dependence. Here is like a optional homework. Use Euler-Lagrange to derive Lorentz force. I think everybody can do that, right? Anybody who has difficulty with that, you just take the derivatives and like set them equal. And if this is the Lagrangian to make the quantum mechanics is formulated in terms of Hamiltonian, and we have to go to Hamiltonian. How do we go to Hamiltonian? We define so-called canonical momenta. Let me write canonical momentum is going to be del Lagrangian, del, let me write it like V, and it is going to be mv minus E over C A. And here you can see this V. Okay, this is, we show it with P. This V is going to be equal to P plus E over C A divided by 1 over M. And typically, this thing this thing we show it with Greek letter P for momentum. So this is P is equal to P plus E over C A, and we call this mechanical. So this is the mechanical momentum, the important one. Let me box it in. And the Hamiltonian, the way we derive Hamiltonian is H. H is V dot P minus Lagrangian, and excuse me, if we do that, what we are going to find is, this is also like trivial calculation, but I see people having difficulty here. I suggest you do this if you have never done this. It's going to be P plus E over C. So this is the Hamiltonian, and I think here I need to have square, which is, you can see, usually we have P squared over 2m. In this case we have P squared over 2m, like mechanical momentum squared over 2m. Also, if you, another thing, like here's another homework, check Hamilton's equations. Let me just write what I mean. So this is x dot is equal to del H del P, and P dot is equal to minus del H del X. And if you do this, what you are going to find is this mechanical momentum is the one that's related to velocity, right? So this is not P but pi. So in the presence of a vector potential, we have to be a little bit careful. Okay, like to get to the important thing, let me give you one more, I think, very nice exercise. I'm personally a fan of these semi-classical approaches because I think they are very nice. But if you're not, you can skip that. Another homework. Use Bohr Sommerfeld, I think Sommerfeld quantization. Let me remind you what it was. It was like B dot dr was equal to nh to show quantization of flux. Flux between two successive orbits. So what this means is, like, there are like orbits that are quantized because quantum mechanics quantizes things. And if you look at two consecutive orbits, one with a radius and one with the next quantized radius, the difference between them is going to be determined by flux quantum. So you can do that if you are interested, but let me just continue and solve the quantum problem. Let's introduce Landau gauge. Landau. So quantum mechanics and physics is gauge independent, but sometimes you can choose a gauge and do the calculation and see what it gives you, and then later you need to think about gauge invariance. And for that I'm going to choose so-called Landau gauge, which is 0 minus b x 0. And if you take the curl of this thing, I think some people can tell me the result before I do the derivation. Can anybody see this? It's going to be, right, and it's going to be along z, but is it going to be plus or minus? And if you do the determinant calculation, this is going to be minus b z. So this is like a convenience factor. So this is convenient. Rather than taking b and the z direction, I'll take minus z direction. Gern-Yang also does that. Either you have this minus sign in the beginning, or you have to carry minus sign all over your calculation. So it's reasonable to do this in the beginning. So Hamiltonian is h is equal to 1 over 2m p plus e over c a, right? And this is squared. And del cross a is equal to b, and this is the same b everywhere, so this is translationally invariant. B is translationally invariant in 2D system, and the electronic system is translationally invariant, but Hamiltonian is not. If you want, by doing this gate choice, you happen to have like a broken translational invariance. But this is not a problem, because if you take x goes to x plus delta x, a will go to a minus 0 delta x b 0. So this is minus delta, and this contribution here can be written as some gradient of like a function, and here this function is going to be delta x b y. So this is like scalar. If you take the gradient, it's going to be vector, and that vector is going to be added to vector potential. And because it has this structure, del cross a, which is going to be which is going to go to del cross a minus del cross del f, and we know this contribution is 0, so b doesn't change. And what this means is like translational invariance corresponds to a gauge transformation, right? Like this translation shift is like a gauge transformation. So you go from one gauge to another once you make this gauge choice. And Hamiltonian is not, right? Hamiltonian seems to break this translational invariance, but it is going to be a correction to phase of the wave function, right? Gauge transformations in the quantum mechanics are manifested as phase transformations. I think we went through this at length. Let me not get into that again, but if you have difficulty, I suggest you go and do that calculation and see how the phase of wave function changes under this transformation. Okay, lastly, okay, it's a good time. Now I can write the Schrödinger equation. A lot of words, but at the end of the day, we have to write down the Schrödinger equation and solve it. So this is h psi is equal to e psi, and here with that gauge choice, h is going to be 1 over 2m px squared. So because of this gauge choice, there is no x dependence here. There's only y dependence here. I mean, y component changes, and the y component changes like py minus e over c is in the vector potential, and there is also bx squared. Okay, this is my Hamiltonian. And as soon as I look at the Hamiltonian, there is x dependence in Hamiltonian, so h is equal to h of x, and x translational invariance is broken due to choice of gauge, but there is no y dependence in the Hamiltonian. I cannot see any y, but y translational invariance is intact. Then I can use this to write the wave functions like psi of x comma y in the form of e to the I ky times some phi, which may depend on k but also depend on x, but no y dependence, right? I can write it like this, and substitute it in the equation. So h psi e psi is going to give me 1 over 2m px squared plus. So whenever I see py, okay, it's here. Let me slow down a little bit. So this thing minus I h bar del y, and if I take the derivative, there's minus I h bar, and derivative is going to bring a factor of I k, and I'm going to have minus e over c b x and squared. And this whole thing is multiplying this phi of k x is equal to e, which will depend on k, so let me write the index phi k of x, and I cancelled e to the I k y's because it did its job, thank you, and we just crossed it out. Any questions? Okay, this is looking nicer, right? It kind of going to look like harmonic oscillator, and when we see harmonic oscillator, we are happy because we can solve it.
So what is k?
So I will come to k. At the moment, k is a parameter that parameterizes this wave function, and it's going to be plane wave wave number, right? Well, let me manipulate this, put it in a simpler form, and then I'll try to come back to k, which will be important. So first, okay, let me rewrite this, not to lose track of what I'm doing. So this minus I is going to cancel this, and I want to write it like p squared over 2m separately. Okay, write it like p squared over 2m, and so this thing 1 over 2m, this is squared, and I want to write it like that. And lastly, I want to take out this e b over c, so this is going to be e squared b squared over c squared. And let me define what was omega. Omega was EB over MC. And from this omega, I want to define a length scale, like L squared is h bar over m omega. Hopefully you did this in quantum mechanics, right? This is the reasonable, if you write the quantum harmonic oscillator problem in terms of this so-called harmonic oscillator length, everything is dimensionless, and you solve the problem in a little bit nicer way without carrying factors. And this thing is going to be h bar over m EB over MC, cancel that. So this is going to be h bar C over EB. So I took out EB over C, right? Then I need to put here C over EB, and I want to put it here. Okay, let me C over EB, but this is HC over EB is exactly the factor I introduced. Let me write one more time. So this is K L square minus X, but I like to write it in the other way. I want, because this is like a square, A minus B squared is equal to B minus A squared. This is going to be X. Let me define it like XK, and this XK is K L squared. Okay, a lot of definitions, but we have to write those definitions on the side of margin and carry them all the time. Here, EB, I want to write it like M squared. There is like M squared, and I want to cancel this M with this M. And here you can see this factor turns out to be 1/2 M omega squared. And I'm also happy because that's the harmonic oscillator. This is 1/2 M omega squared. At this point, we are done because this is exactly like a harmonic oscillator problem, quantum harmonic oscillator, but centered. So usually harmonic oscillator, we center it x is equal to 0, but nobody can force us to do that, right? I can shift the variables any way I want, and this one is centered at xk. And this is the end of the solution. Then as soon as I see this, En of k is going to be eigenstates are, I just copy what I had in harmonic oscillator, and there seems to be no k dependence. And corresponding eigenfunctions, phi and k of x. Actually, let me write the psi, the full wave function, psi and k of x comma y. Up to a normalization, it's like e to the I ky. This is Hermite polynomial, h n x over L minus KL, and there's this exponential factor 1 over 2 L squared x minus xk squared. So this is Hermite polynomial. Good, and the problem solved. Now, coming to your question, what is k? So we need to determine k. For that, I'm going to consider like a rectangular sample. So the length here is, so this one and this one. Let me choose this one to be Lx and this one to be Ly. And because I took in that direction e to the I ky, I can assume periodic boundary, right? There is like translational invariance in the y direction, so I can assume periodic boundary conditions along y, and that means e to the I ky should be equal to e to the I ky plus Ly.
But the translational symmetry was continuous, but now you apply some periodic boundary conditions, so you
Exactly.
make symmetry discrete.
Yes, exactly. Yes, which is what we do all the time, right? No problem. But if you take Ly to be large enough, you can have like very dense k values. Yes, that's correct. And from here, like I look at this, k times Ly should be equal to 2 pi times n, right? This is standard thing we do. And from here, k should be 2 pi over L times n. And n is an integer. So this is first piece of the answer to your question, what is k? But there's also a second piece. So if you look at these wave functions, right, these wave functions are centered at xk, and I'm going to have these wave functions centered at some x of k, and if I have a finite sample, I better have these xk's within the sample. I mean, if it's leaking a little bit out, that's fine, right? Wave function is going to be exponentially decaying outside, but if it's like completely outside sample, that's ridiculous. We shouldn't allow that. Like the center of the wave functions should better be substantially inside the sample. And for that, the way I write this is like 0 is this point, and this xk, let me not include one of them because it doesn't matter, but and the other one is L, I call it Lx. So now let's rewrite this. This one is what? This one is k L squared, and k is this thing 2 pi. Okay, this is Ly. This is 2 pi over Ly times n, and I want to, let me not do this. So now I will multiply everybody with Ly, and this one is going to go, and I will divide everybody with 2 pi L squared, and this one will go. Exactly, and L is bounded, and let's look at this quantity. So Lx, Ly divided by 2 pi L squared is equal to Lx, Ly divided by 2 pi, and L squared was h bar over m omega, and this thing is going to be, rewrite in 2 steps. This is EB over MC. So M's cancel. Multiply with B. This is going to cancel. And this is going to be, the 2 pi is going to cancel this bar of H bar. And this is going to be HC over E. But HC over E is flux quantum. And Lx, Ly is area. Area times B is flux. So this whole thing is number of fluxes. That's why it is like very important quantity from the beginning. Then the values n can be 0, 1, 2, dot, 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 and phi minus 1. There are like in total n phi different orbitals. They are all degenerate, right? Because there is no k dependency in the energy, right? No k dependence. But for a given n is equal to say 0, there are n phi different levels, which are all the same energies. And these are what we call Landau levels. Landau levels. Okay, this n, I apologize, I think this n and this n are different. So this is, maybe I can use m for the second one. Yeah, this is going to get mixed up, so let me call this m. So this is m. So this one is m, and this one is m. So n is Landau levels, and a given Landau level is n phi fold degenerate. And the meaning of this question here, like this, you can see this object. So if you look at that, so we have like some rectangular sample, and inside sample we have these cyclotron orbits of size 2 pi L squared, 2 pi L squared, 2 pi L squared. There are many of these, and actually let me, something like that. And the number of these cyclotron orbits you can fill into an area is given by Landau level degeneracy. Some people are careful, they point out like area should be pi L squared, right? The L is size, okay, this xk is, do I have it? Okay, here. So this is called guiding center. And this L is, the xk is the center of this point. There's like some xk, and the size of this orbit is L, right? Because you have this Gaussian extension. Unfortunately, it's not pi L squared. It is 2 pi L squared. But if you are picky about that, remember to put this factor of 2 here. Okay, let me do one last thing, and I'm going to finish it there. So let's start with 2D and B is equal to 0, right? Let's start with this one. And I want to calculate the density of states. Like the way I do this, like you can do it your way. The way I do this is like this. There's like area times d squared k over 2 pi squared. Right? That's the standard thing. And this is area times 1 over 2 pi squared times, and this is the area in k space, pi, and okay, spinless. Let's take no spin, that's irrelevant, pi k squared. So that's standard expression we write to derive the density of states. But I want to write energy density of state. A is equal to h bar squared k squared over 2m. Then k squared is equal to 2m over, okay, this is squared, h bar squared e. Then n of e is area times 1 over 2 pi squared pi 2m over h bar squared times e. And if I clean up all the factors, there's like area, I think, let me write the area at the end. This is like m over 2 pi h bar squared times area, right? Something like that. And the picture is in 2D. E. Oh, yes, energy, yes, thank you. I almost forgot that. So this is E, and density of states, which we call, let me call it density of states without magnetic field. Epsilon is d n epsilon d epsilon, and it is going to be m a over 2 pi h bar squared. Okay, I think that's the one. And if you draw this, what you are going to find is something like that, right? Constant. So this is d0 of epsilon. This is epsilon. It doesn't, in 2D, density of state is independent of energy, and this is m a over 2 pi h bar squared. Now I want to turn on magnetic field in 2D, and in this case we know what's going to happen. What's going to happen is all these continuum of energies are going to map to this h bar omega n plus a half, right? We derived this, but even if you derived it, you can try to remember this. And in this case, here is the density of states. So what will happen is, like, you have this is h bar omega over 2, n is equal to 0. Here you have h bar omega over 2 times 3, n is equal to 1, and here 5 over 2 h bar omega, right? Something like that. And what we are going to do is, like, right, we are going to take all of these energy points and we are going to collapse them on the closest Landau level. For example, I just divide this by half, and all of these energies here and here, they are all going to collapse to here. All of these and half of here is going to collapse here, and all of these and half is going to collapse here. And what will happen to density of states is like this: dB of epsilon is going to be equal to, now it's going to be, okay, I think I am using En for this. They are going to be a sort of delta functions, epsilon of n's, and they are going to be sum over n is equal to 0 to infinity, and the strength of each delta function is going to be the area here, right? And the area here is m a over 2 pi h bar squared, and the width is h bar omega, right? Hopefully I didn't miss anything. And if you look at this vector, so this is m a over 2 pi h bar squared times h bar omega is eb over mc. So m's cancel, or one of the h bars cancel, the 2 pi and pi cancel, and this is going to be b times a divided by hc over e, and it's going to be phi over phi naught again, right? It's again n phi. So basically density of states is n phi times n is equal to 1 to infinity delta of e minus en. And here is the first simple explanation. Okay, we have seen this order was necessary in the from the this so-called Galilean invariance. We took the boost. We took the boost to a moving frame, and we saw that without doing anything, classical result should be valid in the quantum mechanics. Here, in this case, we have this n phi, and rho yx is equal to h over e squared 1 over nu, and nu is equal to n over n phi. But this n phi is proportional to b, right? If n phi is proportional to b, so this is like a translationally invariant system, then nu is also proportional to b. That means nu 1 over nu is going to increase continuously, right? There is no quantization here, and then rho yx is not quantized, even in quantum description, quantum solution. So we have to put a couple of things to this solution. Let me just give you the advertisement and finish it there. First of all, we need to put electric field along x direction. So this is the simplest one, because electric field is going to be something like V naught times x, and if you add the Hamiltonian Vx times x, right, we are going to go and put here something like some alpha times x, but all we need to do is to complete the square. We are going to complete the square, and we are going to modify definition of xk and everything else. It's also going to be harmonic oscillator potential, but when we do that, E and k is now going to be k dependent. So that's the first ingredient we'll do next time. So that's the trivial one. It's going to be like a 5-minute calculation, but the other two are, we need to put edges, right? Sample is finite, so this is going to be take some thinking. And lastly, we need to put impurities. This is the most difficult one, and I want to take a little bit slow approach to this and show you in detail how impurities map to what we learned in Anderson transition and localization, all that stuff. And then we'll be able to explain why this thing which is not quantized is going to be quantized. Okay, I think let me stop here. Any questions? Okay, thank you.